Hi, ladies and gentlemen. Let me wholeheartedly welcome you to the second session on EC2 E204 signals and systems. The title of today's presentation is Continuous Time Signals and Frequency. So the contents of today's speech are your learning outcomes, then continuous time signals and frequency, then the frequency of composite signals, and the summary of understanding. So your learning outcomes are: you will learn the frequency of continuous time signal, you will understand the meaning of the frequency of a continuous time signal and understand its range. Then you will appreciate the spectrum of a sinusoid, the line spectrum of a sinusoid. Then you will compute the frequency of a composite sinusoid. Then you will appreciate low pass, high pass and band pass signals. So as we saw in the last presentation, continuous signals have infinite number of real values in any arbitrary small interval of time. So since the time axis is continuous, you take any small interval delta t, you can have infinitely many real values for the signal. So the frequency is the number of zero crossings in a second. Say for example, say if there are 1,000, you observe the signal for a second, and if there are 1,000 cycles in a second, then the frequency capital F, that is 1,000 hertz. Throughout this course, I will be using capital F and capital omega for the frequency and angular frequency of the continuous time signal, and small f and small omega for the frequency and angular frequency of discrete time signals. So if you observe 1,000 zero crossings in a millisecond, then there are 1,000 kilohertz or a megahertz, that is a frequency. So inverse of frequency is the time period, that is the time elapsed between adjacent maxima or minima. You observe the adjacent crust or trough. What is the time elapsed between the adjacent crust or trough? That is a time period of the signal. Inverse of that is a frequency of the signal. Say if you look at the sinusoid xt equal to 4 cos 2 pi into 500 t, it has a frequency of 500 hertz and a period of 1 by 500 hertz, that is a 2 millisecond. And when we come to the range of the capital F, they lie in the range minus infinity to plus infinity. And the analog frequency capital F is always unique. Like F, the 400 hertz frequency is completely different from 200 hertz, which is completely different from 1300 hertz. And the angular frequency capital omega is 2 pi capital F. And let us consider a signal. It is not a composite signal. Xt equal to 4 cos 2 pi into 500 t. This is by Euler formula. A cos theta is e raised to j theta plus e raised to minus j theta by 2. So it becomes 2 e raised to j2 pi into 500 t plus 2 e raised to minus j2 pi into 500 t, where j is root of minus 1. So if you look into the first term, it shows a 500 plus 500 hertz frequency, and the second term shows a minus 500 hertz frequency. And the positive, we have no problem with that. There are 500 zero crossings in a second, but this is a little suspicious because we cannot have, we don't count in negative numbers, and we cannot have a negative time. So what is the significance of that minus 500 hertz? So that stems from this Euler formula. It's actually a mathematical fact which necessitates that 1000 hertz bandwidth is required for transmitting 4 cos 2 pi into 500 t. And the spectrum of this signal will look like this. One spectral component at plus 500 hertz that has an amplitude of 2, and one at minus 500 hertz that has an amplitude of 2. So this is the line spectrum of the simple sinusoid, single tone sinusoid. Now we come to the a composite signal that has many tones, like xt equal to 4 cos 2 pi into 500 t plus 2 cos 2 pi into say 200 t. So this has both 200 hertz and 500 hertz in it. Okay, so what is the total time period and what is the total frequency of this signal? So first let us observe a demo with this code comsine.py. Here I open a terminal. I invoke IPython 3. But before I do that, we will look at the code. I'll open it in a text editor. Well, here I have imported two modules, that is a SciPy module for scientific computing and PyLab module for plotting. And I have initiated a time base as an array of numbers. So this starts at 0 and ends at 1 by 200, or actually 1 by 200 minus 0.0001. So every interval is a 1 e raised to minus 5. And x is, the function is 4 cos 2 pi into 500t plus 2 cos 2 pi into 200t. Now if we plot this, we can appreciate this. This line puts a grid on the graph, and show will, it will show the GUI. I will run it here like now we can see the composite signal here. Okay, you can observe the composite signal here. Now it is time to consider the period of this signal. So let me go back to my presentation. The time periods of each sinusoid is T1, that is 2 milliseconds, that corresponds to 500 hertz, and T2 is 5 milliseconds, this corresponds to 200 hertz. If T1 by T2 is rational, then XT is periodic. So that is mandatory. If T1 by T2 is rational, then XT is periodic. Then the total time period T is the LCM of T1 and T2, that is 10 milliseconds. So the frequency of the composite signal is 1000 hertz. This is T1 is 2 millisecond, and this is T2, not T1, this is T2 is 5 millisecond. So we come to the next section, that is based on the frequency component. The continuous time signal can be either a low pass signal, that is here all frequencies are below a certain frequency B. Then there is a high pass signal, here all frequencies are above a certain frequency B. Band pass signals, here all frequencies lie between some predetermined values B1 and B2. So here this is a low pass signal. So if you see here, all frequencies lie between 0 and plus B, and minus B to 0. This is actually the mirror image of the positive side. So this is a low pass signal. And this is the spectrum of a high pass signal. All frequencies lie above B. B to infinity, all frequencies are available. From 0 to B, no frequency is available. And here you see the mirror image of the positive side. And for the band pass signal, from minus B to plus minus B1 to plus B1, in between this range, this low pass range, signals are not present. Above B2 and below minus B2, no signal is present. So all frequencies are confined within B1 to B2, and here you have the mirror image. So this is a band pass signal. Now coming to the summary of understanding, first thing, you understood the frequency of a continuous time signal, that is the number of zero crossings in a second, and you understood its range. The frequency capital F is in the range minus infinity to plus infinity, and so is capital omega. Then you appreciate the spectrum of a sinusoid. You understood the two spectral components in that, and you understood the meaning of the negative frequency. Then you computed the frequency of a composite sinusoid. What if there are more than one tone? What if there is more than one tone in a sinusoid, composite sinusoid? There you have seen that for that composite sinusoid to be periodic, the ratio of the time period should be a rational number. Then you appreciated the low pass, high pass, and band pass signals. And that is the end of this presentation. Thank you all.